So thank you very much for inviting me here. It's been very pleasant and a remarkable conference. So my topic is what if string theory has a de Sitter excited state? And it's, as you may have noticed, it's a kind of an answer to the question that was originally proposed, that what if string theory has no de Sitter vacuum? Saying that maybe it has not a vacuum, but so the study of de Sitter is warming up quite a bit, and a lot of people working on it, and half of the people think that positive cosmological constant solution cannot exist as a vacuum. Other half thinks that positive cosmological constant solution can exist as a vacuum solution, and the remaining people are doing ADS-CFT. So based on the following papers, and Gyadiwali and company has also come up with similar conclusion. They also have similar kind of ideas, so you may want to look at it. So I would first talk about the problems of getting de Sitter as a vacuum solution. And then I will talk about de Sitter as an excited state in the theory. It may be a hard problem, but even if it is a hard problem, I will say that maybe it's a doable exercise. So let's just look at this action over here. This is the typical action you see with the usual thing. If the cosmological constant is positive definite, and these are the additional term you get by dimensionally reducing some theory up to 4 dimension. If this is the kind of action you get, then absolutely there is nothing more to say here. We can just finish the talk here. The problem is that one of the biggest problem in string theory is that this factor actually does not come from free. String theory actually does not have that factor automatically built inside it. So question is that, can I get this factor, that little factor of square root of lambda, square root of g lambda, can I get it from dimensionally reduce some kind of 11-dimensional theory over here? So that is the problem, and the answer is actually yes if lambda is 0 or negative, and the answer appears to be no if lambda is positive. You might think that it's a bold claim. For example, what stops us to actually have a potential in this particular way, where there's a Minkowski minimum and then here is a de Sitter minimum over here. So what is the problem of getting a potential like that in string theory? What will turn out that what we are finding is that a potential like that may not be possible in string theory. What is possible is a potential of this following form with ADS minima. I did not draw the ADS minima, but those ADS that we get are not scale separated ADS. So getting a scale separated ADS itself is a very hard problem. Question is, why is that? To study this, we'll use M theory. So you may ask that we know nothing of M theory, of course. We really don't know much about M theory, but we do know that at very low energy, M theory is given by a certain set of massless fields. So we know their action. But one thing we do know for sure, that even if we don't know the ultraviolet definition of the short distance behavior of M theory, we know that there exists a well-defined theory there. We just don't know the degrees of freedom or the interaction. In other words, for example, if we know a theory that exists in the far ultraviolet, then we can do an exact renormalization group flow and get a theory in this energy regime. In this energy regime, we have all the massless degrees of freedom, and then we have an infinite tower of marginal and all kind of relevant and irrelevant interaction over here. And the coefficients of these interactions are given by these are the Wilsonian coefficients, or the, as Polchinski would say, the exact renormalization group coefficients. And these contains all the information of the far ultraviolet theory. So our analysis will be completely based on this energy scale. We'll never go in an energy scale over here. Here, the energy scale, the degrees of freedom are given by the massless. It's over here. Now, there is also certain subtleties about the off-shell state. As we will see that these off-shell states are given by certain non-local counterterms in the theory that Dieter has also emphasized. And as you also probably know, that gravity, quantum gravity, is a very tricky theory. Most of the interesting dynamics of quantum gravity is controlled by non-local counter terms instead of the local theories. But even though the theory is local, but it's very interesting, even if you want to calculate the Newton's force between two particles, if you do it in quantum field, quantum gravity, you have to use the non-local terms in the theory. Anyway, I'll probably not have much time to talk about this thing. Huh? Good. I'll talk about it. Let me come to that question. So let's see what is the problem. Problem is that imagine somebody gives me a metric of this kind in type 2B theory. So this is, you can easily see, it's a kind of a de Sitter with some internal space over here, and this is in the flat slicing. If somebody gives me this, so I want to do it in type 2B. Of course, I know that type 2B is very difficult because there is no well-defined action in type 2B theory. So we have to go to a simpler model, which is the M theory uplift octave. And if we do that, then this is the condition we get. And here lies everything. This is the flux which we use to get a solution like that. These are the fluxes. These are the brane and an anti-brane. These are all the orientifold plane and all these things are bunched together. This is the cosmological constant. These are the quantum pieces. That's the condition you get after you put all the equation of motions together. If you remove the quantum piece over here, then you see everything is positive definite. If I want lambda to be positive, there is no solution in the system. The system has absolutely no solution. But you see, if lambda is negative, you don't need quantum pieces. There exists a solution. So ADS spaces are very easy to get in string theory. But de Sitter space is very hard. And you see, there exists no de Sitter space with all these classical components. So the only possible way you can get a positive lambda if some of the quantum pieces become negative definite. Now that's a very tricky problem because some of the quantum pieces becoming negative definite, first of all, we are balancing quantum with the classical. That's a complicated problem. And saying that quantum pieces become a negative definite quantity, it's a completely nonsensical statement in the sense that we don't know what is the hierarchy, because what is the hierarchy of the quantum terms and all. So there's already a problem which we already noticed in 2014, that there exists no simple solution, simple way by which you can get a de Sitter vacuum solution in string theory. After that, of course, a lot of paper came showing that there is these things are in the Swampland and so on. Yes, there's some time dependence in the internal fields. We took a very generic construction. You might ask a question about flux quantization and all kind of things. Yes. Late time singularities? Why don't I come back to that one? It turns out that at late time, these things become time independent. As you go to late times, things become time independent, which gets you out of these kind of issues over here. But there are much deeper problems with this setup. Okay. So, it seems like although there is no solution, it seems like there is some good news. Means if I can construct quantum pieces in this particular way, we might be able to get a de Sitter vacuum solution. And in fact, it turns out that with some kind of time-dependent fluxes, you can construct a possible hierarchy in quantum system by which you may be able to get a solution of this particular form. The question is, we can stop the talk right here if this were the case. But what is the problem with that simple assumption that you can solve this? The problem lies much deeper. Because remember, we said that we are studying everything at the far infrared. That means I have somehow integrated out, but as pointed out, that this is actually not an easy process to do. In fact, there does not exist a simple way of doing it. The reason is very simple. There could be two reasons. One is that actually there is no well-defined ultraviolet completion, which we know that although we don't know what is the short distance behavior, we do know that there exists some well-defined UV completion of this theory. But the problem comes that if you take a de Sitter solution and try to study small fluctuation on top of the de Sitter vacuum, you'll find that these fluctuations, the frequencies of these fluctuations are changing with respect to time. And remember what Wilson taught us. Wilson taught us that you integrate out these high energy, high frequency modes. But if you start integrating out the high frequency mode, the modes themselves become low frequency. So there is no meaning of this integrating out procedure at all. In fact, there is no integrating out procedure possible in a time-dependent background. So the question is that you might immediately ask, what happens in a static patch? In a static patch, everything is time independent. Of course, what happens in a static patch? Well, let me give you an example why there is a problem in the static patch. In a static patch, you see that you are sitting in a static patch. So this is some cartoonish way of writing. You are sitting in a static patch and you are taking a high frequency mode over here. And this does not change with respect to time. So you might think that I can integrate it out and write a well-defined effective field theory at low energy. But a person who is sitting in a global patch, he will see something else. He will see that the frequencies does seem to not change inside, but actually the frequencies are changing outside in a global patch. That means the person who is sitting here will mistakenly think that the frequencies are not changing with respect to time, but in fact it is changing with respect to time quite a bit. And this observation was actually, even Banks had an observation a month ago. He found that in a static patch, actually the energy is leaking out in a very interesting way. So how did people deal with that? Of course, there's three ways people I know deal with that. First is, of course, it's just a joke that you can ignore it and assume that space-time is negative cosmological constant. The second is a very interesting way, which Cliff and other people are slowly using it. It's called an open quantum field theory. If you know anything about open quantum, I'm sure you know quite a bit about it. It's a very interesting theory that does not have a well-defined energy momentum tensor, because the energy is leaking inside the system. It was first developed by Feynman and Vernon. And in this case, you actually don't even have a well-defined action. You cannot define things very well. So what you do is that you separate things in terms of environment and degrees of freedom, and you allow energy to be exchanged between them. So, and all the calculation in this kind of open quantum field theory, yes, are done using Markovian process. Yes. Yes, we do, indeed. Normal state in that thing, which you can do it in open quantum field theory. I'll come back to this issue also. Thank you for pointing that out. And the other one is to pose that there is a Transplanckian censorship in the sense that you do not allow very high frequency modes to enter your Hubble horizon. This was developed by Robert and other people. So these are I know these are the ways to deal with this, but what is the problem with that? As I said, that open quantum field theory has this issue, but the problem is to realize open quantum field theory in string theory setup. In a string theory setup, to realize an open quantum field theory is a very, very hard process because you have to separate degrees of freedom in some particular way. You have to determine how the strings are quantized. As far as I know, that this problem has not been done, and as Cliff pointed out that nobody even have tried to realize this. So I'll not go into that direction. The second case, the censorship, Transplanckian censorship, which was originally proposed by Robert and Martin. The reason they proposed it is because they took Einstein gravity, and we know that the ultraviolet behavior of Einstein gravity is sick. So that means all those modes, short distance mode, carry the sickness of the short distance behavior. So when they become low frequency, they become low energy, so they enter our Hubble horizon, and they carry all the bad thing about the UV in our Hubble horizon. So they wanted to put a censorship saying that those modes cannot enter our Hubble horizon, and that restricted the time limit for this. But we know that this is not exactly an issue in string theory because the short distance behavior of string theory is actually not bad. So these UV modes will not create a problem. So putting such censorship is not a way out for our case. What is the way out is that if we view that thing as an excited state over supersymmetric Minkowski background. So that's the proposal we had. In other words, we claim that there does not exist a potential like that, but string theory might have a potential like this with some anti-de Sitter minima over here, and those anti-de Sitter minima are typically non-scale separated. I don't know about scale separated anti-de Sitter minima. Also, de Sitter cannot be realized as a coherent state because, as you know, coherent state capture the classical behavior, and all our analysis showed that classical behavior cannot capture this. So we proposed a new kind of state in this theory, and that state is given by, we take an interacting vacuum in this kind of potential. We take this potential and assume that this is governed by some exact Hamiltonian, and which has an interacting vacuum omega. And we shift that interacting vacuum omega by some operator D. I will specify these things more clearly soon. So this is by definition is, we call it the Glauber-Sudarshan state because these were the people who first hinted towards the existence of these kind of state. And this D is not a unitary operator, but could be Hermitian. So that's our proposal that there exists a state like that. So question is, how do we proceed to do any calculation? So we'll first assume that this interacting vacuum over here is non-degenerate. Maybe can I come back to that question? Ask me a bit later. I will show you a calculation by which you can do it. Yes. Yes, I would say yes. So how do I calculate the metric of my space-time? Well, to calculate the metric of my space-time, I'll use the usual trick. I will sandwich a metric operator between these sigma and sigma. And since it's not unitary, I have to divide it by something over here. So question is, this is just an abstract formula. How does it actually work in real life? So let's take a potential like that. Again, I'm ignoring the anti-de Sitter minima because of certain other reason. Let's assume that we live here. No, these are all Minkowski. I have not drawn the anti-de Sitter. There is some certain reason. Maybe I'll come back later on that. Okay, so let's assume that we are here, somewhere here. And let's call this local minima as zero minimum. So I can express this local minima as a linear combination of the exact eigenstate of the system. I've assumed that this is non-degenerate and there is some energy gap between the excited state. These are not harmonic oscillator states at all. These are some solution of an exact Hamiltonian in the system. Now, how do I extract this thing? We use the usual trick. We hit this guy left and right by e raised power minus I h total t and take t to infinity and along the slightly imaginary direction. And lo and behold, you see that the interacting vacuum can be written as a function of the local minima. The bra is also written by the same operator over here. So you get that particular relationship. And now you plug that thing in this formula. Yes. Yes. So there is one thing I did not tell you is that there is also a UV-RI correspondence saying that there is an infrared cutoff in our theory, which gives rise to a volume structure, which Dieter actually emphasized yesterday. It doesn't really matter. It doesn't really matter, taking the most general case. So you play that particular trick, and lo and behold, you see something very interesting. It converts to a path integral. So the whole system becomes a path integral. If you don't want to see the proof of it, I mean, if you want to see go to Peskin chapter 9, he has actually given a proof of this for a generic situation like that. The whole thing converts into a path integral, but getting a path which shows that the expectation value of a metric is a highly emergent quantity and it's completely off-shell. So we are somehow getting an on-shell background from an off-shell calculation. Okay, and note also that once we have a path integral, all bets are off, because path integral, as you know, is very dangerous because it takes all metric component into account, all fluxes into account, and everything you have to do integrate it out. And that means that you have to take certain non-classical metric also into account. You should also take the complex metric that Witten has recently emphasized, and find the saddle of these things. Anyway, not get into all these things. S total is, let me specify S total. I haven't specified what S total is. Let me specify S total right now. So we haven't exactly specified what is S total. Let me give you how it looks like. It should be, one would expect that it is actually a low energy limit of M3, but it's actually slightly more complicated. But before I go into it, let me tell you that where are the non-perturbative effects coming here? How do we calculate the non-perturbative effect? The non-perturbative effects are coming from the fact that once you do a path integral calculation of a If we know what is S total here, if we do a calculation taking a simple model, you'll find that this system is asymptotic, which in other words, the path integral does not converge, and therefore you have to Borel resum the whole thing. Once you do a Borel resummation, then you will see that there is a non-Potawave effect automatically coming in. This is exactly what Steve Shanker showed, how D branes appear in this kind of set. There's also further pop-up ghost and all these kind of complicated structure. I'm never relying on perturbation theory. This is an Euclidean action, but only taking the polynomial sector of the with the higher order terms, all the higher order terms. Why don't you look at it and tell me whether it makes sense? So question is that what kind of action I should take as S total? So here is a proposal. We can write S total in this particular way. Note that this is the zero instanton sector of this theory, and then there is a fluctuation determinant. You have one instanton sector, there is a fluctuation determinant. So in other words, you can write it in this particular way, which is called the trans series way of writing the action. So this is the kind of action you should take to determine. And note that this is far away from what the usual perturbative analysis would have given you. On a given saddle, not a vacuum, on a given instanton saddle. Different vacua, because the potential can have different vacua. I'll give you one concrete example how to compute this thing. Okay, so this will be the typical form of the action over here. So how does it look like? We'll take a simple scalar field theory, and I'll try to show you how this thing is done. So let me now tell you how exactly we get this kind of state. So imagine I want to, again, go back to the same thing. I want to get this kind of metric over here. So I know that doing it in type 2B theory is a little bit tricky because there is no simple type 2B action by which I can actually get this. There is no well-defined type 2B action. You know, all this problem with type 2B. So we lift it to M theory. In M theory, it looks like that. So all these factors just reassembles itself into this particular way. Now, what are we claiming? We are claiming that concentrate on this factor over here, these factors, time-dependent factors. So we are claiming that the expectation value of these, our metric operator should look like that. Expectation value of these internal metrics should take this particular form over here. So the claim is that once we take the Glauber-Sudarshan state, and if we manage to do this path integral calculation, then we should be able to express this expectation value in this particular way. And you can see that although these operators are non-zero, their expectation value becomes 0. So we now see that these on-shell degrees of freedom that we expect are appearing from a completely off-shell computation. And in fact, in our model, there are no on-shell degrees of freedom. Everything is off-shell in this analysis, and everything is emergent. Okay, so there is no on-shell, everything is emergent quantities over here. A somewhat similar conclusion Ghia Diwali and other people also are getting. So it's not gauge invariant. I don't want at this point to put any gauge invariance in the theory, but when I actually do so we impose the gauge transformation. By doing gauge transformation, you can actually make these kind of things 0. But in an actual calculation, the gauge invariance appears as this ghost in this, or the pop-up ghost in the path integral. Huh? I didn't hear you. I'm imagining gauge fixing and for the pop-up ghost over here. Okay. So if you want to check these kind of thing, I mean, I think here Ion Company had somewhat similar answer. Anyway. Note also that if we are actually not, I haven't really emphasized string theory because I'm just doing a simple scalar field model and claiming that this is the case. But if we use the actual string theory, we would have an instanton going as e raised to the power -1 by g string to the power of c. If c is 1, you know that these are d branes. If c equal to 2, these are ns brane. If c is other, there are other instanton For C equal to 1, Steve Shankar and all showed that you can get it by a trans series of this particular form. But to have a convergent series like that, we need G string to be smaller than 1. And it turns out that if you impose this type 2A G string to be smaller than 1, you get a bound on the time in this particular way. And if you have been following some of these papers and all, you know that this has been proposed to be the Transplanckian bound. It's surprising that despite of us not using any Transplanckian censorship and all, we are getting the same bound. So we got this bound by employing this. Diwali and all got a bound by saying that such coherent state can exist for there is a quantum breaking of coherent state that leads to this. And Robert and all got by imposing that there is a Transplanckian bound on that one. Yes, 5 minutes, okay, nice. Okay, so how do we get the dynamics of this system? And you know, to get classical behavior from quantum mechanics, you actually have to do Ehrenfest equation. And here you have to get the, yes. Five minutes later, yeah. Right. So it turns out that the equation of motion now takes a very interesting form. Instead of del S total by del G, we know S total is that trans series stuff over here. You get this expectation value equation of motion. This you have recognized is the Schwinger-Dyson equation. The question is, can we bring it in some useful format, and how do we are dealing with off-shell component? Well, I will not have time to say anything about off-shell component. So you can actually bring it in some useful format, and if you define some perturbative series in this particular way, then you can show that the equation of motion, and then this action, as I was asking, the action takes this particular form. So you see this is the usual supergravity piece over here, and then there is at S equal to 0, you have this whole perturbative series that yesterday Dieter was emphasizing. But then it's at the zeroth saddle of the instanton, then you have at the first saddle, you have another, and so on. So there's an infinite series of this particular way, and then there is some non-local piece. So this is the typical low energy action that would look like. We don't know the coefficients of these terms, but this is the most general kind of piece which you can expect. And this is how the equation of motion looks like. You see, it's not R mu nu minus half G mu nu R, but R mu nu of an emergent quantity minus half of some emergent quantity are equal to the energy momentum tensor. Good luck with solving that kind of thing. So, but that's how it looks like. The behavior of the system take this particular form. Now, let me answer one last question that I've been claiming that you get a trans series. How do we see that we get a trans series? Let me take a simple scalar field model and explain to you. Let's take this simple scalar field model, and let's assume that D is given by that particular thing. And I'll claim that expectation value of phi is somehow related to the G00 that I said, and I'll claim that this is, we expect that expectation value of phi should take this particular form. So how do we do this calculation? We put it inside a path integral. Here is how we put it inside the path integral. This is the measure, this is the action of that. And remember, you see that the action is shifted by a quantity because of the fact that I have chosen the coherent state in this way, and sigma is the parameter of the coherent state, phi is the field. So this is how it shifts over here, and this is the lambda phi 4 expanded over here, and this is the source piece. So this is the expectation value of phi. And the bad thing is that you cannot terminate this series anywhere, because perturbation theory is not good theory to study quantum field theory. Actually, you have to go beyond perturbation theory. So now let's look at this at nth order, how this looks like. At nth order, you see this is the measure, this is the action. At the nth order is g to the power of n factorial 4 to the power of n, and then this is the field over here. Now, if you play the game properly, you can show that. I'll discuss this later. At nth order, the theory, the Feynman diagram in the model grows in this particular way. You see, this is a factorial growth, showing that this perturbation theory that we are studying is actually not convergent as you expect. We got rid of infinities, one kind of infinity we got rid of by renormalization. Now a second kind of infinity has appeared in quantum field theory, and that is called the factorial growth of that. So now we see that's why we cannot ignore anything in quantum field theory. The mistake people do is that we ignore things in doing this calculation. We should not ignore any perturbative series to any order actually, because the system is not convergent. So you see there is a nice growth over here. So that means the path integral takes this particular form. This is nth order. This is how it grows, and these are some coefficient, and this is the piece from the source term. So now I can resum this whole path integral because this piece I can resum it. And if I resum the whole thing, lo and behold, the whole thing become a closed form. So this is the piece which comes from the source term. We still don't know what is sigma over here. And this is the Borel resummation of the whole thing. And we take the principal value. And you can easily see that no matter what sign A takes, there is only one pole in the Borel plane. There's only one pole in the Borel plane. So you can, the Stokes lines are very simple. You can sum over all the Stokes line and you can actually do this integral. And something nice happens over here. No matter what sign is you take, this quantity in front of it is always positive definite. Okay? So this quantity becomes positive definite and you get a completely closed form expression for this whole system. Of course, the final answer is like a wave function renormalization of the whole thing, but that's not important. And this summation is developed originally by Borel and later on by Ekal. So now it's called the Borel-Ekal resummation process. Okay, so you can also check the following thing, that if you actually expand it, you can get exactly the instanton saddle and the fluctuation determinant around it. So the system does have instanton, number of instanton over here and the fluctuation determinant. And that's the reason why everything is written in terms of a trans series. So now, what do we want? So we want this. We got that. So this is what we want over here. What we got after doing a path integral calculation is this. So maybe we can claim the following thing, that maybe this quantity is proportional to that, and that t to the power of minus 1/3 coming from this integral. If that is true, then we can determine what sigma coherent state we need to reproduce this factor. And this quantity is related to that. Of course, there's a much deeper reason for splitting it like that. There's a much deeper reason why we split it in this particular way. But I will not have time to tell you about the deeper reason. You can look it into our paper. There are multiple reasons why this split makes sense. So this fixes the value of these, what kind of coherent state we need to reproduce a factor like that. But now it gives something very interesting. It gives, for the first time, a closed form expression for the cosmological constant. So this is the piece we get just from a scalar field model. You see that no matter, as I told you, no matter what we do, this quantity is always positive definite. So whatever we got has a positive definite in front of it. So this must be something with a positive cosmological constant. Question is that, can this be made small? That we don't know. It's a work in progress because we actually haven't been able to evaluate this integral because it involves all kind of principal value calculation. But question is, can this be as small as this? We don't know. We have no idea whether it can be very, very small quantities. Definitely proportional to m Planck square. And there is all kind of factor coming in over here. So I don't want you to get to alarm because we actually haven't solved the cosmological constant problem. We actually taken a scalar field model where we showed that there is a possible way to express this whole series as a convergent analysis. But it gives us a very important deep thing, at least to me, that maybe the cosmological constant is an emergent quantity. We cannot see at any order in the perturbation theory. It could be that the cosmological constant is a highly complicated material which comes from, after summing over all the Feynman diagrams, you get a quantity which is emergent and positive definite. So at any order, we'll never be able to see this quantity. If we did not know how to do Borel-Ekal resummation, we would never have got this idea that there is a positive cosmological constant in the system. So at the deepest level, the asymptotic behavior of quantum field theory or quantum gravity is very, very important. Well, of course, first it was shown by Dyson, everybody ignored it. And then it was shown by Steve Shanker, then nobody ignored it, actually, no people listened to it. But now we are seeing the deeper aspect of the subject, maybe that it's not, everything is an emergent quantity here. The equation of motions are emergent, everything is emergent, and the system behaves like this. So there is always a Minkowski vacuum in string theory or ADS. And whole idea of positive cosmological constant does not come from a minima, but it comes from some emergent calculation in the system. So we'll never be able to see this kind of system by imposing any bound on the potential or not, because it's not the usual way it's appearing in this theory. Anyway, this is our take on the subject. And very interestingly, we find something here that if I have a quantum system in this way, we are past, okay, so I'm done now. Yeah, the summary of my talk. So this is the summary of my talk. All the vacuum configuration are replaced by, you see, de Sitter is replaced by this state, Transplanckian bound is replaced by that, black hole replaced by another state, equation of motion becomes Schwinger-Dyson equation, on-shell state become off-shell state become this, Feynman diagram replaced by nodal diagram, space-time metric replaced by that. Everything has their own counterpart over here, and moduli stabilization replaced by that, no Boltzmann brane, 7 brane, etc., get replaced by certain thing like that. So there is a counterpart of this as an emergent quantity. So I strongly feel that maybe this is the way de Sitter appears in nature. That's all. Why do we have square root of lambda? Because we take the dimensionless quantity as root lambda t. So it turns out that if I have G string, type 2a G string is proportional to root lambda t. If G string is smaller than 1, that takes t going to minus 1 over root lambda 0. Because we are taking flat slicing, the time goes from minus infinity to 0. So that's the reason of root lambda appearing. Okay. That's Hubble time. It's not exactly the scrambling time. Yes, so it's some factors here and there. But we all agree on the general, yes, sorry, yes, sir. Oh, that's it. So we did not know how to show that. So we ran to our nearest mathematician friend in our department. So he gave a proof in our paper. We have a proof. So you have to actually calculate the principal value integral. So if you have done a little bit, so if you have a Borel plane, and there are singularities on the Borel plane, so you can go by this path like that. And the principal value calculation is not just the residue at the pole, but you take one path like that, you take another path like that. So you take one path like that, you take another path like that, and average over all these things. So this is called the principal value. That's how Pikal gave up. So if you do that, you can show that this is always positive definite quantity. If this were negative, all the program would have failed completely. Yes. Yes. Yeah, that's right. At deepest level, it's that action that we showed is actually a string field theory action. Everything, yes. Yeah. Right. Yes. Right. Yes, we don't know how to do that, so hence we go to scalar field theory model. Yes, but answer is yes. Not only that, we have to also take complex metric, because as Witten recently emphasized, that there are also complex stuff also. Yes, yes, I completely agree with you. I know. That's why we resorted to scalar field calculation. Yeah, but as you said, it's very ambitious thing. But some hint is coming. Some hint that the asymptotic nature of a perturbation theory. Now I tend to appreciate more that non-perturbative. We always throw non-perturbative effect, but now we know why the nature has non-perturbative effect. Oh, we compute. Oh, yes, yes, yes. Yes. So let me give you the answer to that question. As you correctly pointed out, we don't know exactly how it's growing. We do know it's growing. We do know it's growing. It's growing. So what we did is that we assume that the growth is n factorial to the power of alpha, but alpha we have no idea what it is. It's bigger than 1 maybe. Okay. So then, as Borel and Ikal showed, that the growth of this is equivalent to the growth of like that. So this is the, anyway, you can look it up, all these things. So this is called the Gevrey growth. Instead of a Borel growth, it's called a Gevrey series. So there is a huge literature on that one. And then you can, instead of summing this, which is much harder, you can sum that guy. And that is what Ikal has developed. You can sum that guy and then you can show. But the problem is that, as you said, we have absolutely no idea how the things are growing. There is no perturbative parameter in M theory, but we don't need the perturbative parameter. What we need is that we need simply the M. So we did everything in terms of M Planck. Sorry. Yeah.